University of Campinas, UNICAMP. In this talk and the subsequent, I agree, I combine with the talker to reduce the presentation in about five minutes. Then the next presentation, in this one, the presentation is about 20-25 minutes. So we can have time to lunch and return to the next session in afternoon. Thank you for accepting to participate as a speaker of this event, please.
Thanks, Damasceno, for the kind introduction. It's a pleasure to be here, to meet old friends, and former students, and even a former professor. I think Professor Nosek doesn't remember, but he was I was one of your students in adaptive and array signal processing at TUM. It's like 15 years ago. So. And so it's a pleasure to be here. I was a professor here at UNB for 6 years, and I consider here as my second home, or my first home. So I really feel home here. Thanks a lot for the invitation. And the topic of my talk is Space-Division Multiplexing in future optical communication systems. And this work, I have to acknowledge the contribution of my 3 students working on the topic, Omar, Alaioso, and Layusun. And this is the agenda of my talk. I'm going to say a few words about our labs, ComLab, and then go to the motivation, some flavors of space-division multiplexing for optical communications, and some of our contributions. But since we don't have much time, I've just show just 1 or 2 slides about each topic, and then finish with the bibliography. I'm part of the ComLab. I'm from the University of Campinas and UNICAMP, and I'm part of the School of Electrical and Computer Engineering. And if you wish more information about our lab, it's the Digital Communications Laboratory. There's this website, ComLab.com.br. And we have great students coming from different parts of Brazil and also different parts of other countries. Like we have 2 Colombians, 1 Indian, 1 Spanish, and 1 from Ecuador or Ecuador. And we have like a very active group of master and Ph.D. students. Now, let's start with the motivation. So I'm talking about space-division multiplexing for optical communication systems, and I would like to use a large portion of my talk just to explain why this is important, or why is this becoming important right now. And for this, I'd like to propose you an exercise, which is let us suppose one point-to-point link of an optical fiber, which supports 80 wavelengths, and also, actually, let's talk about an optical cable. And the optical cable, they have several fibers inside, and let us suppose an optical cable with 12 fiber pairs per cable. But we say fiber pairs because we need 1 fiber on the way and the fiber to bring the traffic in the way back. And those fiber cables, they usually carry 80 wavelengths or better. Like every cable can carry several fibers. And in this example, we have 12 fiber pairs. And each fiber or fiber pair carries 80 wavelengths to both sides. Okay, so this makes the capacity of fiber link. So we have a fiber cable. Inside the fiber cable, we have fiber pairs. And each fiber pair carries several wavelengths. And what I show here is that at the beginning, we use just 1 fiber of the fiber cable, and at the beginning we used just one wavelength of the 80 wavelengths available for each fiber. And let us suppose that this system started operating in 1995. So it is like 20 years ago. Okay, so 20 years ago we started with just one wavelength of one fiber of one cable. And in that time, the capacity, the demand capacity was 1 megabit per second. And, but now there's an important issue, is that traffic keeps increasing exponentially every year. I mean, it's true that the exponential of the growth rate changes over time, but the traffic is roughly exponential. The traffic growth is exponential. And let us suppose that now to easy our, to make our life more easy, let us suppose that the traffic increases 100% in a year, which is high, but okay, this is just to show you well, the problems or why we need space-division multiplexing. And so in 1995, we started with a capacity of 1 megabit per second, and 96 with 2 megabits per second, 97, 4, and so on. And you reached 2001 with a demand of 64 megabits per second. And if we suppose that that those traffic are served by transceivers using 10 gigabit per second, we ended the year of 2001 requiring actually still just one wavelength of one fiber of one cable. But the traffic kept increasing, so we ended 2005, like after 10 years, the traffic increased from 1 megabit per second to 2 gigabit per second, but still we just needed one wavelength of one fiber of one cable. And now we reached 2009, and something very important happened. What happened in 2009? The traffic demand increased to 16 gigabits per second. And instead of using just one wavelength, we started using two wavelengths. Like, this was something important. Like, after 12 years, then the first or the second wavelength was activated. And this is interesting to see that the whole fiber infrastructure in this whole growth of internet from 1995 to 2009, it didn't change much. And therefore, we are used to getting ever higher traffic growths without paying much. Actually, we used to pay less every year. And this actually was possible because the whole infrastructure for long-distance transmission or even submarine transmission also didn't change much. So the operators were able to even reduce the price of service for increasing data rates. And but traffic kept growing, increasing, doubling every year. So from 2 wavelengths, it required 4 wavelengths in the next year, in 2010. But in 2011, something important happened, is that instead of using the so-called on-off keying for transmitting information over the fiber, we started working with coherent communications and higher order modulation formats. And this change of paradigm, it was really a quantum leap for optical communications, made it possible to get a roughly 4 times increase in spectral efficiency. So that in 2011, we went back to one wavelength of requiring just one wavelength of one fiber of one cable to carry the whole traffic. But traffic keeps growing exponentially. So in the next year, so that this whole change of paradigm gave basically 2 years, relief from this increase of for this traffic growth problem. So, and then traffic kept increasing, and in 2015 we got to a required demand of 1 terabit per second, 2 terabits per second, 4 terabits per second, and then next year, this operator in this exercise will have to activate the second fiber in the cable. And this is important, but it's interesting to see that we spent 10 years basically using just one wavelength of one fiber. But after we fill in the capacity of this wavelength, we start increasing the number of wavelengths exponentially. And this is important because even like the number of transceivers will also start increasing exponentially. The footprint of the equipment also grows exponentially, as well as the power consumption. So this is an important thing. And when we got to this point here, then the situation becomes even more dramatic, because if we spent 20 years using just one fiber pair, the next year we are going to need 2 fiber pairs and then 4 fiber pairs. And then the situation becomes worse in 2022, where we're going to start doubling the number of cables per year. And therefore, space-division multiplexing is very important for optical communications. Like, it can be that our whole information society may have to change, because we're used to it. If you think of our model of operation, it's quite weird that we pay for a bit to transmit a bit from Brasilia to Taguatinga, or from Brasilia to Japan. We pay basically the same thing. Like, we pay access per bit, and not according to the distance that the bit propagates. And this has been possible only because of the cost per bit has been decreasing, and only because we have been reusing the same fiber infrastructure. But this will change very soon. So therefore, we need technologies to cope with this in such a way that the number of fibers, or now we can call better spatial dimensions or spatial dimensions, increase, and the cost doesn't increase at the same pace. Like, we don't wish our costs to increase also exponentially. And this curve shows the number of spatial dimensions required to support traffic in a point-to-point link with a start occupation of 30%. Like, let's think that in year 0, we require just we have a 30% of the link occupied. As the traffic evolves, the number of spatial dimensions also grows exponentially, and this leads to the so-called capacity crunch of the optical communication systems, because this crunch happens when the number of spatial dimensions required to transmit traffic also starts to increase exponentially. Of course, the example I gave to you is quite dramatic, because it assumes a 100% traffic increase over year over year. And of course, this is not true in every portion of the network, but it's true in some portions of the network. And this is, I borrowed one slide from a Google presentation at the Optical Fiber Communications Conference in 2017, and the topic of the presentation were like capacity limits, when or where, and they say the following: that the traffic increase or the traffic growth rate strongly depends on network demand, on their growth, and the data center to data center and data center to user traffic are both experiencing strong growth. And the cloud technologies only reinforce this trend. And the Google network already requires multiple fiber rails per link. So the Google network in some parts are already in the position of increasing the number of fibers exponentially. And this is true for long haul and subsea. And this is especially important for subsea systems because they are very expensive to install. And this might be soon true for metro as well. And the scarcity of fiber for long haul and subsea makes capacity a more immediate issue. And they finished the presentation saying that, or this is a copy of a slide actually. They end the presentation saying the capacity crunch is real and we are experiencing it. So then we have a problem that it's good for us, like we have work, we're engineers, we love to solve problems. And then, so we need to support space-division multiplexing. So it's not enough anymore to optimize the capacity of a single fiber, because we are close already to the limit, to what we call the channel limit for the optical fiber. So we are going to need to exploit more parallel paths to convey the information over over long distances. So, and which are the solutions which are being proposed for space-division multiplexing in optical systems? This is the first technology, which is to use fiber bundles. So we consider space-division multiplexing the use of parallel fibers. And operators are already doing it. So we can say that current systems are already operating with space-division multiplexing. But of course, there are more interesting technologies, which are, for example, multi-core fibers, which are fibers, spatial fibers, which share the same cladding, but have multiple cores inside. And another technology are the few mode fibers, and this is I think for us it's the most, maybe it's more ahead in time. Maybe it takes many more years to become a commercial, but this is for researchers very interesting, which is the use of few mode fibers for long distance transmission, or even short distance actually. Few mode fibers are basically multi-mode fibers. And the problem of multi-mode fibers is that they have several modes, they support several modes, and every mode is a separate channel, orthogonal channel. And so it's possible to do MIMO, to launch several signals over the fiber and detect them and separate them afterwards, probably using DSP, using signal processing. But those fibers are not the multi-mode fibers we are used to work with. They are special fibers containing just a limited number of modes, because like current multi-mode fibers work with hundreds of modes, and these few mode fibers work typically with maybe up to 6 or even 12 modes. And these multi-core fibers, they can come also in two flavors, what we call weakly coupled fibers or strongly coupled fibers. Like in weakly coupled fibers, like the cores of the multi-core fiber, they are made apart such that they don't interfere. And so light is propagated as if we had multiple single mode fibers. But in the strongly coupled, but the problem here is that if there is any crosstalk from one core to the other, then transmission may become infeasible. And another solution is the strongly coupled cores, in which the cores are more close together. So there is crosstalk among them, but then we need MIMO to separate the signals in the end. So here we come close to a multi or a few mode fiber. It's very similar, but the architecture is different. There are some advantages of doing this core separation, especially for exciting the different modes. over the fiber. And another interesting feature, I'm not going over all these details here, but there is an interesting feature which may not be common to the wireless communications people, which is the following. Like, if we had like two modes, and if you don't have any coupling between them, the delay spread is very high. But if there is a weak coupling between the two modes, then there is some coupling, so there is some part of the green signal going to the red one and vice versa, and the delay spread is bad and the coupling is also bad. But if you have a strong coupling in the fiber, then the delay spread becomes smaller, which is not so obvious, I mean, but it's interesting that, so we should either, it's better either to keep these two modes separated and try to separate them without MIMO, but if there is some mixing, it's better to have them strongly coupled to reduce the delay spread. This is one interesting feature of optical multimode. And then nowadays we have just a WDM wavelength vision multiplexer to mux the different transceiver signals of the different wavelengths. And then in the future, we are gonna need also a space-division multiplexer, multiplexing the signals of the different modes. And or we can do vice versa also, to multiplex the different modes and then the different wavelengths. But this is a little bit more difficult to implement. Now, going to very briefly to our contributions on this field. I'm not going deeply onto the details, but just to say that we have working on the switching architectures for the different solutions for networks operating with wavelength division multiplexing and mode division multiplexing. There's a conference paper published this year in cooperation with Stanford University. We are working, this is interesting, I think, especially for this workshop, because it merges the problems of communications networks and power systems. That what's happening is that we are investigating the impact of mode division multiplexing on the submarine links. And in submarine links, the power available to feed all the repeaters which are under the sea, the power is limited. And there's usually just one power feed cable. So if we start having several parallel fibers, since all these signals, they're periodically amplified, there's not electric power to feed all the repeaters along the link. So then we come to conditions like this, where if we increase the number of fiber pairs, the capacity of the link doesn't increase linearly with the number of fiber pairs. Like if we double from 20 to 30 the number of fiber pairs, the capacity of the link just increases marginally, because we don't have, we can increase the number of cables, but there's not power to feed all of them. So this is an interesting problem, which also, we also have two papers this year on this, also in collaboration with Stanford. And the third line of operation has been to research also MIMO systems together with a filter bank multi-carrier for optical systems. And we have also a paper, a conference paper this year, also in cooperation with Aston University in the UK. They're providing us the channel models for this. And I think I'm not going too deeply on this, too much details. These are some references of also from our papers. Like these two are about submarine systems with Omar, and with people from Stanford, and also from Layuson, our Ph.D. student, in cooperation with Austin University. And I'm open to questions now. Thanks a lot.
Thanks, Professor Darli. Now we pass to question to audience, please. Please.
Thank you for that very nice talk. I think one problem in the future will be that all those techniques which have been developed for MIMO in wireless to be transported to the optical system at a much, much higher data speed which is there. So the problem in general is we have very sophisticated algorithms in wireless which work for, let's say, 100 megabits per second, maybe a gigabit, but now we're talking here about terabits or even above terabits. And that may be a really big challenge for stripping up those algorithms such that they are still implementable at those high frequencies, those high data rates, and they will be also power hungry then.
Yes, exactly. I think you touched several important points, and I think the complexity and high-speed implementation is definitely one of the main issues. That's why we are, in this last slide they showed, we are mentioning this subband transmission, so that each subband could be treated separately. There are some conditions of the wireless signal which cannot be directly translated to optics. For example, depending on the systems, we can have delay spreads of several hundreds of symbols, which makes like techniques such as OFDM very hard to implement because it would require a cyclic prefix, which is huge, and also power consumption is also another important or very important issue. Therefore, there are some people starting to look at techniques to implement the MIMO in the optical domain, like all optical with virtually no power consumption. But I must say that this is still really preliminary, and maybe in the future with a quantum computer or something like this, there are better alternatives. But thanks for the comment, very, very interesting.
We have time for another or one question. Please.
Thanks for what you have shown. Is there any solution available for the problem of power consumption? Anything already thought?
No, this is, yeah, nowadays, I think from a very practical perspective, what people are trying to do is to find a compromise between performance and power consumption. Like usually we are used to evaluate the best algorithms with offer the best performance for the systems, the largest reach. But now people are looking a little bit how to set up the best trade-off between power consumption and performance. So sometimes it's better to allow the system not to be the best one, but to use algorithms which are easier, which are less computationally expensive. But power consumption is definitely the one major topic on this issue.
We close the presentation of Darli.
Thanks a lot.